past, so we can get cracking with Nora's talk. Nora is an assistant professor at Siena College. She was a research engineer in a nuclear physics lab at the University of Washington, and has recently revised the Stanford Encyclopedia entry on theory and observation, co-written with James Bogan. She has a book manuscript under contract with Cambridge University Press entitled The Epistemology of Experimental Physics, which is coming out at some point later this year. She's also the author of the article Evidence Enriched, which gives some sort of account of her empiricism. And from the sounds of it, she'll be talking about some similar stuff today and elaborating on that a little bit. So without further ado, I'm going to hand over to Nora, who is going to be presenting empiricism with enriched evidence.
Thank you. Excuse me. So today I'm going to sketch an account of empirical evidence that I think applies to science and practice, data production, processing, analysis, and all, which nevertheless retains an epistemically significant distinction between the empirical and the non-empirical. So I'm going to argue that an empiricist who embraces this view of evidence can both account for how we learn about the natural world through scientific investigation, and for the myriad sophisticated methodologies that empirical scientists actually employ in their work that have little to do with human perception. So as we've seen throughout this conference, there's a variety of empiricisms in the history of philosophy and in contemporary scholarship. I think there's a common thread. For me, the heart of empiricism is the necessity of experience for learning about the world. So to learn about the natural world, we must submit our conceptions to the tribunal of experience, right? Empiricism in this sense stands in opposition to rationalism. So we don't gain knowledge about nature via contemplation in absence of experience. And I think this isn't empty posturing. Every so often, even today, scientists themselves raise the possibility of doing science proper in the absence of experience. Such possibilities are particularly tempting, it seems, in contexts where scientists are investigating parts or aspects of nature where it's becoming difficult to get more empirical data, right? Where scientists are coming up against the limitations in the empirical access that they have to what they'd like to study. In such contexts, scientists sometimes reach for other resources in the hopes of keeping scientific inquiry moving forward. If we're running out of empirical evidence in some domain, there's no more data to collect, or we don't see a way to collect the data we want, scientists begin to wonder if perhaps we might adjudicate theories based on other virtues alone, like parsimony, elegance, explanatory power, and so on, in the absence of empirical evidence. So this occasional flirtation with the possibility of adjudicating evidence in this way within the scientific community is, I think, just a manifestation of the old empiricist rationalist debate. And I think empiricists should oppose such epistemic shifts every time they arise and insist on a continued critical role for empirical evidence in the adjudication of scientific theories. So let me just give you one very quick example of a moment of this sort where this kind of rationalist possibility has recently been raised by the scientists themselves. So in investigating the early universe, the very early universe, cosmologists do seem to run out of data they would like to have. In investigating the very early universe, cosmologists can use the electromagnetic spectrum to get pretty far back in time. Maybe neutrinos and gravitational radiation can take us a little bit further. But it seems, that at some point there's a causal horizon beyond which we're not going to be able to access more information. One fairly clear case of cosmologists instantiating a shift towards non-empirical methods is the defense of the eternal cyclic cosmology offered by cosmologists Paul Steinhardt and Neil Turok. So according to this theory, our universe lives on the surface of a higher dimensional space, a brain, and very close in this space, there's another such brain that periodically collides with our own, thereby causing successive Big Bangs on the order of every trillion years. The basic scenario is as follows. The brains collide as a result of a spring-like force between them, and the potential energy associated with this force is positive when the brains are very far apart, which causes the expansion of the brains themselves to accelerate. But because of the nature of the spring-like force, eventually the brains collide again, and this cycle repeats eternally. So it's kind of this amazing cosmogony story of like the repeated coming together of these brains, right? So the eternal cyclic model that I've just described is indistinguishable in principle from a finite cyclical model. The claim that the cycles are similar, periodic, and occur eternally cannot be favored over a non-eternal cosmology by observational or experimental evidence, even in principle. Instead of appealing to empirical evidence, Steinhardt and Turok offer some kind of non-empirical support for their theory by claiming that the eternal cyclic model has significant explanatory power. Namely, it explains why there is a dark energy component in the energy density of the universe. In particular, they suggest that the eternal cyclic model naturally provides dark energy a key role in cosmic history. And the best reconstruction that I can muster of this explanation that Steinhardt and Turok offer is as a kind of teleological explanation whose telos is the eternal nature of the universe. So consider this quote in which these cosmologists invoke their eternal cyclic scenario to explain the presence of dark energy. They say, the cyclic model leads naturally to the prediction of quintessence and cosmic acceleration, explaining them as essential elements of an eternally repeating universe. In other words, if we're to have an eternal cyclic solution, which must be conceptually desirable for other reasons, then our theory must have some component that blocks inhomogeneities from accumulating across successive cycles, because if the theory predicts that they do accumulate, then it's falsified by the apparent homogeneity of our observable universe on large scales. And dark energy is just the sort of thing that dilutes these inhomogeneities. So in other words, if dark energy is present, then a cyclic universe of the eternal variety is possible. So the power of this teleological explanation is apparently supposed to provide support for the eternal cyclic model. Now, I think that a teleological explanation that assumes a priori preference for eternity cannot help us discern which cosmological theories are viable candidates for the way the world could be, and cannot serve as a replacement for empirical evidence we wish we had in order to keep science moving along. So I've said that the heart of empiricism is its commitment to the necessity of experience. We must submit our conceptions, our theorizing about nature to the tribunal of experience in order to learn about nature. But what is the tribunal of experience? To what is our theorizing accountable? With respect to what exactly should our theories be empirically adequate? Empiricism has traditionally emphasized the primacy of human perceptual experience in the project of learning about nature. So the traditional empiricist worldview is something like this. Like there's the natural world on the one hand and human theorizing about nature on the other. And the way that we get our theorizing into alignment with the way that the world actually is by adjusting our theoretical understanding in response to our observations, that is, to our perceptual experiences and paradigmatically what we see. And this traditional idea that our knowledge of nature bottoms out in observation does not accord well with science and practice, as many other folks in this conference have already said. Much of our best science has disastrously little to do with observation by the human eyeball. When we look at scientific practice, in actuality, we see instead complicated instruments, techniques, processing, and what at the end of the day our scientific theories are constrained by are often the results that come out of sophisticated data analysis pipelines. The process of making naked eye observations, like gazing at the moon, just isn't a good model for imaging a black hole accretion disk with the Event Horizon Telescope, for instance. So the details of this image's provenance are quite complicated and particular. To get this beautiful image of M87 star's accretion disk, the collaboration starts with radio data amalgamated from several different stations around the globe. The data is then processed using a suite of presuppositions, including like the distance to M87, a geometric Earth model to precisely locate the stations with respect to one another, a clock model to synchronize the data across stations, corrections accounting for Earth's atmosphere, and so on. In the telescope, the system of telescopes produces this patchy data, and the full image that you see before you has to be reverse engineered from that patchy data. The collaboration tried different plausible scenarios, plausible options for reconstructing the image, and these ended up yielding different results. And in the end, they developed a few different imaging pipelines, which they had optimized based on their success in reconstructing known synthetic images. And the empirical data were then run through each of these various pipelines, blurred to a common angular resolution, and then averaged together to produce the final images of M87 star accretion disk that we saw on the front page of the New York Times and everything. So even from this very brief discussion, I hope it's clear that this resulting image is produced by a long chain of processing, and itself has accreted an extensive halo of assumptions and presuppositions that contribute to making it what it is. Even further, to get from this image to an estimate of the mass of the black hole presumed to be at its center, the collaboration has to make further assumptions. In particular, they had to invoke models that already take on board theoretical assumptions from general relativity and magnetohydrodynamics. To check the consistency of this empirical result with the general relativistic accounts of black holes, the researchers have to invoke a lot of assumptions that leave their imprint on the result and in part constitute how it turns out. And I think this sort of story is ubiquitous in science in practice. It's not just the Event Horizon Telescope, it's really everywhere. So what kind of empiricist epistemology of science can account for this? In the 2018 paper that David mentioned in his introduction, I argued that empirical adequacy is adjudicated with respect to what I've called enriched lines of evidence. So the idea is that generically, there's some process of data collection that produces data records, then typically data processing that transforms those records into a result that can actually be used to constrain some theory. So for instance, the process of reducing a set of images from a digital telescope might involve correcting each exposure by performing bias subtraction, flat field correction, bad pixel masking, then calibrating each exposure astrometrically and photometrically, modeling the point spread function of each exposure, remapping each exposure to a common coordinate system, co-adding the exposures and so forth, right? And there'll be metadata associated with data collection, which I've called the provenance metadata, and metadata associated with the data processing, which I've called workflow metadata. And metadata are just the auxiliary information about how the empirical results produced in data collection and data processing are generated. So for example, in volcanology, to take an example from a different field of science, the provenance metadata might include geographical information about where particular rock samples were collected, and workflow metadata might include information about corrections for atmospheric contamination of certain isotopes that would otherwise confound the potassium-argon dating of the rock sample, right? And note again that in order to generate an empirical result that's appropriately formulated to constrain some particular theory, for example, to calculate the empirical value of a particular parameter or to produce a proposition, much more processing than just sort of preliminary data reduction techniques will typically be required. So my view is that the empirical adequacy of scientific theorizing is adjudicated with respect to lines of evidence enriched by auxiliary information about how those lines were generated. And by lines of evidence, I just mean a sequence of empirical results, including the records of data collection, and all subsequent products of data processing generated on the way to some final empirical constraint. And by auxiliary information, I mean the metadata regarding the provenance of data records and the processing workflow that transforms them. So together, a line of evidence and its associated metadata compose what I'm calling an enriched line of evidence, and the evidential corpus is then to be made up of many such enriched lines of evidence. So you might be wondering, why does it have to be this complicated? This sounds like a beast. Right? Why can't, for instance, the final empirical results just serve as the evidence with respect to which our theories are to be consistent, right? The problem is that bare empirical results considered apart from their metadata are not good candidates for explicating the tribunal of experience, that with respect to which our theories ought to be consistent. Because the evidential corpus composed of empirical results is internally inconsistent. And it would be a fool's errand to require our theories to be consistent with something that itself lacks consistency. So time and time again, it looks like science produces result R and then promptly not R. Here's a plot from the particle data group showing measurements of the mass of the Eta meson from the 1960s through the present. Some of these measurements fall outside of each other's error bars, and so taken by themselves appear inconsistent, right? However, the collection of empirical results considered together with the auxiliary information about how they were generated is not internally inconsistent, just as there's no contradiction between if X then P and if Y then not P, even though there is one between P and not P. So we really need to consider not just bare empirical results, but empirical results considered together with their associated metadata. And I should say, however, that although the presuppositions that contribute to the generation of empirical constraint are implicated in the epistemic utility of that constraint, in practice, the entire enriched line of evidence need not be hauled out for appraisal every time a result gets used as a constraint on some theorizing. So for instance, researchers may have good reasons to believe that the instrument used to collect data was well calibrated without going and explicitly checking all of the available information relevant to that calibration. However, new reason for them to be suspicious of the instrument's calibration could of course arise later on, and revisiting that information would then become epistemically imperative. Okay. So in my 2018 article, I argued that viewing empirical evidence as enriched in this way helps us to understand otherwise puzzling questions. Questions like, how can evidence accumulate across theory change? How can evidence produced in different experiments be combined together and used jointly? How can the same evidence be used to constrain competing scientific theories, right? And indeed, I argued that it's not despite the assumption-riddled character of empirical results that these feats are accomplished, but rather in virtue of it that they're possible at all. To see why, it helps to note that to serve as a constraint on scientific theorizing, an empirical result must be well adapted to the context of constraint. In other words, the result has to be presented in a form amenable to the theory to be constrained, right? So given the myriad assumptions that get baked into an empirical result throughout the course of data production and processing, and the fact that empirical results need to be couched in conceptual and formal trappings that are recognizable to the theory to be constrained, the issue of whether a particular result is well adapted to serve as a constraint in some context is no idle matter. We'll say that an empirical result is well adapted when either all of the presuppositions incorporated throughout data collection and processing are formally compatible with the theory to be constrained, or their incorporation doesn't make a relevant difference to the constraint. To take a very quick example, my calculation of the dark matter contribution to the total energy density of the universe based on empirical data from galaxy surveys cannot straightforwardly serve as a constraint on your new theory of cosmology if dark matter is not even among the ingredients of your theory, right? But this means that when researchers have access to enough background information, that is enough metadata, empirical results need not be ossified in their original form. It can be possible to unwind the processing that results have undergone and reprocess them to render them newly well adapted to a different epistemic context. In this way, the epistemic utility of empirical results can transcend radically diverse contexts. So even if a result is initially maladapted to some context, by appealing to metadata, it can be possible to make it well adapted. So to take a favorite example that I've been thinking about recently, ancient Babylonian eclipse records inscribed on cuneiform tablets have been used to generate constraints on contemporary geophysical theorizing about the causes of the lengthening of the day on Earth. And this is surprising and kind of awesome, since the ancient observations were originally recorded for the purpose of making astrological prognostications. Nevertheless, with enough background information, the records as inscribed can be translated, the layers of assumptions baked into their presentation peeled back, and the results repurposed using the resources of the contemporary epistemic context, the likes of which the Babylonians could have hardly dreamed. So while it's true that the epistemic utility of empirical results depends on the details of their provenance, and those details are often extensive and particular, this doesn't necessarily render evidence tragically local. Rather, with sufficient metadata, the epistemic utility of empirical results can be revived in new contexts. So on this view, observation per se is irrelevant to the empirical nature of evidence. the fact that the output of scientific instrumentation eventually needs to make a transcranial journey in order to be of any real epistemic interest ought not to mislead us into thinking that, the empirical is best understood as the observable or sensible. The interesting questions are not about observability, but about empirical access, and observation is neither necessary nor sufficient for access. Empirical data and empirical results are imbued with theoretical assumptions, but these assumptions are an important part of what makes the theory appraisable possible. The enriched view of evidence supports the idea that it's not despite the intertwining of the theoretical and empirical that scientists accomplish key aims, but often in virtue of it. And furthermore, being imbued with assumptions does not prevent us from repurposing empirical results and putting them to epistemic use in new contexts. In addition, this view makes the epistemic value of metadata, encoding the various assumptions that have been made throughout the course of data collection and processing, explicit. The desirability of explicitly furnishing empirical data and results with auxiliary information that allows them to travel across epistemic contexts can, I think, be appreciated in light of the objectivity norm, right? Construed as accessibility to interpersonal scrutiny. So when data are repurposed in new contexts, they're not only shared between subjects, but can in some cases be shared across radically different paradigms, even those with incompatible theoretical commitments. But what makes data empirical in the first place? What does it mean for something to be empirical? An empiricist position ought to be able to distinguish the empirical from, for instance, the virtual, if it's to remain faithful to the heart of empiricism, I think. The tribunal experience ought to originate from the world, lest empiricism lose what makes it distinctive from rationalism. So I argue that data are empirical with respect to some target, when there's an interpretation of the provenance of those data, using resources of an epistemic context, such that the data are products of causal interaction with that target. So an epistemic context, in the sense I intend here, is just the collection of conceptual, theoretical, and representational resources from the perspective of which the data is to be interpreted. It's important to note here that data are empirical relative to a target. Without specifying a target, it's impossible to say whether some particular data set is empirical or not. Data are also empirical relative to an epistemic context. And the epistemic context supplies the resources with which the data are interpreted. Data never speak for themselves, right? But always rather require interpretive resources. And in particular, they require background theory to furnish a causal story connecting the worldly target of interest to the data collection and recording process. So an important feature of the view of empirical data that I'm defending is the causal production of data. And as I said, to be properly empirical, data should have been produced by causal processes that connect the worldly target of research to the process of data collection and recording from the perspective of the epistemic context in which the data are to be interpreted. There's no perspective outside of an epistemic context from which the causal processes can be identified and traced. Indeed, there's no perspective outside of an epistemic context from which a worldly target can be identified in the first place. Yet, using the resources of an epistemic context, it can be possible to answer the question, were these data produced by causal interaction with the target? And this view of what makes data empirical obviously relies on the notion of causal interaction, which for philosophers is a notoriously fraught notion. And I'm not committed to any special theory of causal interaction. In fact, I believe that this view of what makes data empirical is probably compatible with a variety of ways of explicating the notion of causal interaction. And I think that's the sort of thing that's best left to precise explication within a particular epistemic context using the resources of the background theory in play. So to see why causal production matters, let's consider a characterization of what makes data empirical that eschews causal production and relies instead on ostension. So I'll suggest that this view suffers from a serious drawback. It's not easy to see how it could be applied to data sourced from far away worldly targets that no one can point to in an act of ostension. The characterization that I want to consider comes from this insightful and philosophically valuable paper by Matthias Kaiser from 1991 titled From Rocks to Graphs, The Shaping of Phenomena. And in this paper, Kaiser develops an abstract characterization of the epistemological structure that carries scientific reasoning from what he calls observable reality parentheses data to empirical phenomena. The basic elements of an instance of this structure are what he calls anchor points and inference tickets. And roughly an anchor point is the bit of the world that sourced the data, and inference tickets transform the data by redescription and other operations licensed by theoretical resources. And although Kaiser goes on to formalize these intuitions, so anchor point becomes zero structure and so on, the gist of the idea is as follows. The zero structure consists of the objects of scientific inquiry, this is a quote, together with the simple act of presentation. My basic intuition here, says Kaiser, is that scientific data rest on raw material that can be presented or reproduced upon request. It is essential that this level is kept as simple as possible, e.g. this rock here, or these spots on the screen there, or in social science, these filled in questionnaires, etc. The zero structure contains all those things that are to be subjected to scientific scrutiny, i.e. that are to be measured, weighed, radiated, diluted, accelerated, etc. So on Kaiser's view, what makes data empirical are these original and reproducible acts of ostension, like this rock here. As I hinted at above, I think Kaiser's view is ill-suited to faraway targets in virtue of his Pinterest account, right? On his account, when the material specimen is not present at hand, the scientist cannot anchor the data to it via acts of ostension like this rock here. Instead, on this account, she's forced to anchor her data not to the worldly target of interest, but to some intermediary, as in these spots on the screen there. So let's just consider an example of this sort. Here's a visualization of data from the Arecibo telescope, RIP, displaying spots that can be interpreted as radio signals from distant galaxies. And on Kaiser's account, what makes the data visualized here empirical is that they can be picked out by ostension, by some scientist gesturing at the image, these spots on the screen there. This approach locates the empirical at the site where some bit of the world is present to the perception of a human inquirer. In this case, the spots in the image are what is present to the inquirer. But this approach seems to me to miss the point. The data displayed here are empirical with respect to galaxies. They are data encoding radio frequency emissions of galaxies over time in virtue of being produced by the interaction of electromagnetic radiation emitted by those galaxies, traveling through space and interacting with the receiver of the Arecibo telescope, and subsequently the rest of the readout apparatus of that instrument, right? So in determining whether some data is empirical or not, we should ask two questions. What is the worldly target of research? What is the worldly target that the research seeks to investigate? And what is the data the result of causal interaction with? And this is going to get me into all kinds of trouble with Kareem's cases, and that's why I want to talk to him about other examples at some other time. If the data has been produced by causal interaction, that we can trace from the worldly target using the theoretical resources of the relevant epistemic context, then I think we can call this data empirical. It could, of course, still be poor data. However, if construed from the perspective of the epistemic context in which researchers are working, the production of data is not derived from a causal interaction anchored in the worldly target, as construed by the epistemic context, then the data cannot be empirical with respect to that target. Empirical data may have been produced by observation, more generally by detection or intervention, but not, for instance, by modeling or computation alone. So far I've argued that an empiricist philosophy of science that wants to accommodate much of science in practice needs to make sense of the abundance of sophisticated instrument-aided detection, collection, and processing. And I suggested that this can be accomplished by adopting an enriched view of evidence, according to which the tribunal of experience is understood as the growing evidential corpus composed of lines of evidence considered together with the details of their provenance. Unlike bare empirical results, enriched evidence is cumulative across theory change. And by appealing to metadata, empirical results can be repurposed in new epistemic contexts. In other words, this view of evidence helps show how it can be that empirical results are both theory-laden and also escape ossification in the original context of their production. So I've also presented an argument for what makes data distinctly empirical that relies on causal access rather than observation per se. To conclude, I just want to highlight a few features of this broader empiricist philosophy of science in which I locate this view of evidence. So I do think that we have good reasons to be anti-realist in the following sense. I don't think we'll ever be in a position in an epistemic situation that would justify a belief that a particular theory is true. Rather, we'll only ever be in a position to judge that it's consistent with the available evidence so far as we know. So this is an anti-realism that maybe sounds a lot like von Frassen's anti-realism. The distinction for me is that what von Frosten wants empirical adequacy to happen with respect to is different than what I want it to happen with respect to. In particular, I think, so for von Frosten, it's anything that's like observable, but I think our theories, are empirically adequate with respect to the evidence that is actually available to us. Thankfully, that evidence is growing. Okay. So I think that the appropriate epistemic attitude to take towards to a live theoretical option is just to say that they are empirically viable for now. Of course, scientists choose to pursue certain theories for all kinds of reasons over and above their empirical adequacy, but such reasons are not justification for believing that the theory is true once and for all, right? Nevertheless, I endorse a view of genuine epistemic progress in science. So let me try and explain how. I argue that scientists accumulate empirical evidence and that they also gain knowledge of a certain indirect sort about the way the natural world is. So in particular, they learn that viable theorizing will have to be consistent with the enriched evidential corpus. So in other words, well, in my view, scientific knowledge is not to be understood as like knowledge that a particular theory is true, or the knowledge given to us by a particular theory, or that any particular model will continue to be fruitful, or even knowledge that the truth is somewhere in the landscape of viable theoretical approaches, even if it cannot be singled out. Instead, I propose a shift sort of in the target of our usual epistemic commitment away from theories towards empirical evidence and to the constraints that they pose on viable scientific proposals. So empirical evidence is durable in the sense that there's an onus on any viable framework to furnish a way of understanding the evidence in a consistent manner. Enriched evidence accumulates over time and is relevant across multiple successive and contemporaneous contexts. The accumulating evidential corpus provides continuity between researchers such that even old evidence bears on contemporary models. As the corpus grows, the interpreting scientists have to like carefully wend their way through this ever-thickening labyrinth of evidence. So beyond the mere accumulation of empirical evidence, scientists come to know that any realistic understanding of the part of the world being investigated will have to be consistent with that evidence, right? So rather than coming to know specific theories, they come to know the outlines of possible theories. Nevertheless, in filling in the outline, scientists continually learn about what the natural world is really like. So I couldn't resist trying to fit my view into David's schema. So I hope I've done it justice here, and I'm sure he'll tell me if I haven't. Out of gratitude to David for organizing this fantastic conference, I've tried to place myself in his framework. So he considered two types of empiricisms, right? The epistemic and the methodological, and encouraged philosophers of science to pay more attention to the latter. And his rendering, if I understand it correctly, the epistemic approach is individualistic, anti-metaphysics, theory-led, philosophy first, and influenced by skepticism, while the methodological approach is not so individualistic, doesn't foreground sense perception, doesn't banish all metaphysics, is method-led, practice first, and doesn't truck in skepticism. And the view that I'm advancing here is not particularly individualistic and doesn't admit a central epistemic role for human perception. On the issue of metaphysics, I think I'll need to hear more from David about what he has in mind. If metaphysics is the stuff whose presumed nature is such that we cannot put ourselves in causal contact with it, then it won't be helpful for distinguishing between the empirical viability of theories. If metaphysics is just the stuff that we can't perceive with our human senses, but can gain other empirical access to, then there's no problem with it from my view. Similarly, I'd like to hear more about what David means by theory-led and philosophy first. On my approach, theorizing is certainly involved, but so is scientific methodology and practice. My view is in some sense influenced by skeptical concerns, or perhaps better epistemic humility, but my view is anti-realist, but I think that there's an important indirect way in which we learn about nature through the accumulation of empirical evidence. That's what I've got for you. Thank you.
Thanks so much, Nora. That was really fascinating. And yeah, thanks so much for including that table with reference to the talk yesterday. So I'll go through questions, prioritizing students. So Christopher, if you want to start off.
Thanks. I learned so much from that. Quick clarification.